There he is.
Oh, perfect.
Yeah. Okay, thank you all for coming up here. I'm pleased to begin the proceedings for Srijan Das's final public oral defense. Am I doing it right?
Yeah.
I'd like to just begin by a very brief introduction, saying that Srijan came to us from the Indian Institute for Science and Scientific Education in Kolkata, and has been with us for 5 years. And the work is going to speak for itself. I'll show it to you. When I first did pick up the thing that was in Cheryl's office, I had that reaction, like the one immemorialized of Donald Trump looking at the sun, because I was blinded because volume 1 on the front, but that was actually a clerical error. And this is the whole volume, okay? But nevertheless, it's an impressive piece of work. We talk a lot about expectations for graduate students. You know, this is meets or exceeds expectations. Okay, so thank you for meeting and exceeding expectations. Srijan has done a number of studies. He will tell you about them. Most of them are published, and we will learn a lot. I would like to introduce the members of the jury. Furthest away at this point geographically is Professor Hanna Soga from the Tata Institute of Fundamental Research. Thank you for being here or there. Professor Lisa Bünye from the Institute for Science and Technology in Austria, in Klosterneuburg, Vienna. And Professor Amitava Bhattacharjee from Astrophysics and PPPL at Princeton. And the main advisor is Professor Jeroen Tromp, who you all know, and who is with us remotely from his sabbatical location. Thank you. Srijan, please tell us what you did.
All right. Thanks, Frederick. Hopefully I'm audible over Zoom. So, as the title says, my thesis is called Magnetoseismology of the Sun and Inferences of Solar Rotation using Normal Mode Coupling. I will sort of decompose the title soon as we go along, but to start with, just one second. Okay, so to start off, I would try to show 3 representative images of what is going to build on the study. The first picture over here is essentially an animated view of the inside of the sun, along with some copper fields, copper wires, as you see, that's sort of representative of the magnetic fields, large-scale ones. And then there are 2 cross sections showing certain colors, and those are essentially the flow profiles inside the sun. The central image is something that really motivates me behind what I'm doing. And this was shown to me the first time when I went to the Max Planck Institute in Germany, and I was shown by Sami Solanki, and I was asked to find which side is a simulation and which side is an observation. So I'll give all of you a couple of seconds to decide which one do you think is a simulation and which is an observation. If you have guessed it right, the one on the left is a simulation and the one on the right is an observation. And the fact that they're so close, and yet we know nothing about how to image or how this structure, which is a sunspot, looks like underneath, is sort of startling. And so that drives me towards trying to find, can we devise methods, or can we actually find how magnetic fields under the sun looks like? And finally, the image on the right, which I'll come to in the second chapter, is essentially something that Frederick made in a project that I worked on later, which is about basis functions which you can make up for any random patch. In this case, it's a cat and a duck. So to start off, I thought where else to begin than where we all thought how the sun might look like when we were as a kid. So this is probably how I drew it when I was a kid. It's not my drawing, but I'm sure this is very similar. And now moving forward, when I went on to, let's say, like junior school, I started looking at the sun from my house. This is literally a picture taken 3 days back by my father from like the playground just beside my house. So this is how the sun looks like, and this is how I looked at it for approximately 18 years of my life before I came here. And so moving on from here, when I went on to school, we sort of started learning about things like, the sun is the center of the solar system, and there are planets around it. It was 9 back then, right now it's a little less. And so the Earth is habitable because of this Goldilocks zone, where the amount of radiation that you get sort of balances out the coldness versus how hot it should be, and the fact that it has carbon dioxide at a certain amount, so that global warming happens to sufficient amount to sustain life to approximately, let's say, 18 degrees centigrade on an average. And then the fact that the Earth is a little tilted with respect to the ecliptic plane of the sun, and therefore we have seasonal variations. Moving forward, when I went on to high school, we sort of learned a little bit about the Renaissance and how Galileo drew these images of sunspots. And if you put together 36 of those images, you can form a sort of nice imagery of how the sun actually moves around, and the sunspots track the movement. However, these things are called sunspot, but they're pretty large. I got to know this later, but the size of a sunspot is almost comparable to the size of the Earth. Some other random numbers over here. So the Earth is approximately 93 million miles away from the sun, and the sun is very large. We can approximately fit 1.3 million Earths inside the sun. However, we're pretty far, so that won't happen anytime soon. And it takes like 8 minutes for lights to come from the sun to the Earth. So whenever you're looking up at the sky, you're looking in the past. And then in my first year of undergraduate, I came to know about this fact that the sunspots are not really fixed on the surface. They move, and they also vary over time. And so what happens is the sun starts from a minimum where there are very few spots on the surface, and then slowly they increase over time through a solar cycle, reach a maximum, and then decay again. And this sort of marks the magnetic activity of the sun. And in these images, although we cannot see it, the sun is actually threaded by magnetic fields all over, not just the sunspots. And these are the large-scale magnetic fields that you can see. And these are responsible for some of the solar storms and events that we also feel on the Earth. However, all of these things are invisible. I learned in my advanced years of my college or undergraduate that you can use complicated methods from plasma physics and magnetohydrodynamics to extrapolate and start visualizing and seeing what you couldn't see by naked eye, except during solar eclipses, when you can actually see the plasma frozen onto these lines. And when the sun is directly blocked by the moon, these lines illuminate. And so this is sort of a direct evidence of the fact that there are magnetic fields spreading out of the sun. And these fields are the coronal field lines. And in a very nice observation, we can see how, when these magnetic fields that I showed you sort of twist and turn and interconnect and reconnect, it results in these eruptive events which release a large amount of energy and throw out matter such as plasma as well as magnetic field, and which are sometimes directed towards the Earth. And when they finally reach the Earth, they have drastic effects on the magnetosphere, which can be felt by looking at the auroras, these brilliantly colored lights near the poles. And these are also very critical for satellites which are high in altitudes and astronauts, as well as telecommunication, which could result in large blackouts if there are extreme events. And finally, all of this that we are feeling at the Earth or seeing in the solar atmosphere is rooted in what's happening inside the sun. And this is a nice animation from the very first slide, as I showed you, showing how the flow field inside the sun drives the magnetic fields, which in turn has a feedback on the flow fields. And this is manifested in the surface as modulation of the magnetic activity, which shows up as the number of sunspots fluctuating over time. So if we start from 1996, which was the solar minimum, we'll see that the sun was visibly inactive, which means there are very little flares or these bright spots which show up when reconnections happen on the solar surface. And then slowly, as you progress to approximately 5 years down the line, you see that it lights up, and this is the solar maximum, and then it fades back again. So what we saw right now can be summarized as the sun is our closest star. It makes the Earth habitable. However, a large part of what we see happening on the sun happens due to magnetic fields and has drastic effects on the space weather. And everything that we talked about right now sort of roots back into what's happening inside the sun, which is why it is important to study the interior of the sun. When I came to Princeton and I started my PhD, that's until then I knew how to look at the sun using different methods. But when I started doing helioseismology, that's when I started to understand how to listen to the sun. This image that you see here is how helioseismologists look at the sun. And these different branches show which frequencies we can hear the strongest. I'll break down how to read this image in a few slides, but that's where we start. Okay, so let's go on to helioseismology now. So helioseismology is defined as the study of the solar interior using the surface pulsations. So if we look at the surface, we see how it's moving or pulsating, and from there we try to infer what's going on inside. The way we do this is by using satellite observations. These are from the SOHO MDI observations, one of the NASA ESA missions. And so the image on the left shows you a Dopplergram. And if you're familiar with the word Doppler, you would know that anything that's moving towards you is blue shifted, and anything that's moving away from you is red shifted in terms of wavelengths. And we can look at pixel by pixel of these disk images, and we can see which pixel is moving towards or away from us. And from there, we can figure out how the surface is pulsating. And from there on, we can devise methods using the physics that we know to understand what's happening inside. The image on the left shows a raw Dopplergram image, and you can see that one side is very dark and the other side is slightly bright. And this is because the sun has a large solid rotation. So one side which is moving towards you is clearly blue shifted, and the one which is away from you is red shifted. If you take off the mean rotation rate of the sun, what remains is the image on the right. And that's what we sort of work with when we try to find what's happening inside the sun other than the solid body rotation. An important concept in all of this, and that I'll sort of gloss over here and not talk too much in the later slides, is the concept of using basis functions. So you know how when you have a string of a guitar, you pluck it, and you can sort of see how the sines and cosines can make up any sort of random pattern on the string of the guitar. But that's in 1D. However, the sun is a 3D object, and the surface is a 2D sphere. And the basis functions we use for a 2D sphere are spherical harmonics. In this image, I'm trying to convince you that you can add up all these differently colored spherical harmonics and make up any random patch on a sphere. If you haven't been convinced yet, let's look at this. So we know how the cosmic microwave background looks like, which is almost a random patch on a sphere. What I'll show you here is that as we keep on adding more and more spherical harmonics, we'll finally end up with the cosmic microwave background. So we can use spherical harmonics as an efficient basis to decompose what's happening on the surface of the sun, as well as trying to figure out layer by layer what's happening inside. And whenever I speak about spherical harmonics, you should imagine these different modes which are pulsating, as I show here. If you add up all of these different pulsations using sufficiently weighted coefficients, you would end up with what you observe as in the sun over time. So these are called the solar modes of oscillation. So what have we learned till now? We take the Dopplergram, which are pixels moving away from you and towards you, and then we decompose these Dopplergrams into spherical harmonics. For each spherical harmonic, we can see how the amplitudes vary as a function of time in the central image. And then if we take this particular image and we do a temporal Fourier transform, you would end up with the image that I showed you first, and that is what contains the most amount of information condensed in one image. So the way to read this is, in the x-axis is the level of complications of these spheres that I showed you. So the higher the number, the more complicated is the geometry on the surface. And on the y-axis, these ridges show you which are the frequencies at which these modes pulsate the strongest. And so you can pick up a mode from L equals 400, which pulsates at, let's say, 2 millihertz, and add up with all the other modes that you have to get the complete picture of how the sun looks like. Yeah, technical glitch. So how do we study what's happening inside? What I showed you here is like, how you take the observations and decompose into an understandable picture. So as we go towards higher and higher angular degrees, which is in the x-axis, what that does is it can be compared with these rays or modes traveling through the solar interior. For the lowest Ls are the modes or the waves which penetrate right through the center or very close to the center. And these are the low angular degree modes. And these are the spheres which have the least complicated geometry. However, as we go towards higher and higher angular degrees, we see that the modes are confined closer and closer to the surface. So if we choose a low angular degree mode and a high angular degree mode, we can selectively study the deeper interior versus the shallower parts of the sun. So now that we know all about helioseismology, let me show you what I have done.
Is it possible to ask a clarifying question? You're showing ray optics way near the surface where the shear is very strong. The usual assumption of ray optics is, as you know, the scale length of the number is long compared with path of propagation. Is there any problem in sort of using ray optics so close to the surface?
So when we start off with a background solar model, which does not have any of these things. And what all the complications that you're describing are first and possibly much higher order corrections, which I don't think is possible yet in the resolution of the solar instruments that we have right now. So because we are using background solar model, I think this works fine. All of that happens when we start taking into account much higher complexities, which possibly has very low implications on the observations. So going on, I have 5 chapters. The first one is essentially asking the question, can we measure the full 3-dimensional large-scale magnetism using helioseismology? And the main takeaways from that is, are we going to find sensitivity kernels, and can they be used to measure internal solar and stellar magnetism? The second thing that I did was to extend the global picture and try to see if we can selectively find the smaller scale fields closer to the surface, which are more relevant to direct space weather events. The third is that, okay, we now understand how theoretically to measure magnetic fields, but do we need to make corrections to the flow profile? Because the ultimate signal that we measured, the cumulative effect of all perturbations, is flooded with measurements from signal from differential rotation. And so if magnetic fields are very weak compared to differential rotation in how they show up in the observations, the first thing we need to ensure is the strongest signal, the perturbation that causes the strongest signal, is that adequately measured? So that's what I do for the next 2 of my chapters. And finally, I use the theory of my second chapter, and we try to find how the flow profile looks like under supergranules. So supergranules are, if you look at any random small patch on the sun, you can see there are these small convection cells, which are actually pretty large. They're 35 megameters large. And each of these cells can then be averaged to make an average supergranular picture. And so what we try to do is, can we find the flow profile under an average supergranule? There are 5 chapters, and I do not have that much time, so I will talk about only the first 3 of them. So this is my favorite example and possibly my favorite part of the presentation. Let's imagine that you have your coffee cup, and you know exactly what the coffee is composed of. And so what we are interested in is to find what is there inside the coffee. So if you pretend that when you fill up the cup, you know exactly what's in there, then you put a drop on the surface and you look at these ripples. You can compare those ripples to what you expect using what you know about the coffee, and they will match exactly. However, if you then put a little bit of sugar in the coffee and it sort of goes down and settles somewhere, and you put another drop, it'll have ripples, and these ripples are not going to match the ripples that you had the first time. And the reason is that you have something more going on in the coffee than what you already know. In the next phase, you add a little bit of cream and it settles somewhere closer to the surface. And you'll see that it's going to be even more different from what we saw for just the sugar. So all these small differences that you cannot account for from just the background coffee that you originally knew, are the differences that you're interested in finding. So can we find the density of the sugar? Can we find the density of the cream? And that is exactly the questions that we ask for the sun. If we know the background sun, which is the coffee that you took initially, and we know exactly what it is made up of, and then we make the sun a little more complicated. We add rotation, we add magnetic fields, and then we try to see, does the pulsations on the surface, do they match with what we expect if it was just the background standard reference sun that we imagined in our minds? And of course, they don't match. And the amount of differences in these pulsations or the ripples that you see on the surface really depends. They really depend on where these perturbations are, so where the cream is, where the sugar is, because what happens is the response or the sensitivity of the system to something that is closer to the surface as compared to something that is further deeper is different. And these sensitivities are essentially captured by these analytical functions called sensitivity kernels. So we can see that if F is the frequency that we measure on the surface, and if B is the perturbation that we have in the interior, which we want to measure, what we really need is the yellow line, which is the kernel. In our case, in my first study, my goal was to find what this yellow line looks like for magnetic fields for the sun. And it is all related through a simple relation, F equals K times B, which actually, in our case, it's a little more, it looks a little more complicated than just that, is that we have observations, and that is related to the perturbations which you want to find through the kernels. And our background sun is something which looks very boring. So this is the most boring picture of the sun I could find on the internet. And the background or reference sun is spherically symmetric. It is not rotating. It is not magnetic. It is adiabatic. It is isotropic. It is static. It's like, yeah, it's extremely boring. So the next question is, the observations that you make from the real sun will not match the theoretical predictions from this sun. And these differences is what is going to capture all the perturbations that are not accounted for in this boring sun. The reason differential rotation is known this well until now is that the kernel, which is this mathematical object I've shown at the center, is known very well for many years. And so we can start our observations. And by observations, I mean how much that red line differs from the black line, which is the difference from the first set of ripples to the next set of ripples that I talked to you about when you add sugar. So the shape of that red line as compared to the black line are these differences. And these are called frequency splittings. If you know frequency splittings, if you know the kernels, then you can find what the perturbation looks like. And that's why we know very, very well how differential rotation looks like. However, the kernels for finding 3D magnetic fields for the sun was not known until my first paper in my PhD. This doesn't mean that there were no efforts in that direction. There were, of course, efforts by Goff Thompson, Zimbowski, Goudet, and many by Callie and Schunker. However, most of them were forward calculations, which just means that they made up magnetic fields of a certain shape, and they asked the question, okay, what is the pulsation that we'll observe if this was the magnetic field? This is a forward calculation, and there are many non-uniqueness in this problem. You can make up various kinds of magnetic fields to produce similar pulsations on the surface. However, it's only when you know the full kernel can you actually ask the question, okay, given a certain observation, can we formally invert for how the magnetic fields look like? And that's where we come in. So I will not expect you to know these equations, but these are the equations for magnetohydrodynamics. What the first equation means is, how does plasma, which is ionized gas in the sun, how does it move in the presence of forces such as magnetism, such as gravity, pressure forces? And now that we look at a plasma moving, how does, when it moves, how does the thermodynamics change? That is the second equation. The third equation is, as the plasma moves, as electric charges move, it also has a feedback on magnetic fields. So not only does the magnetic field affect the charges, but the charges also affect magnetic fields. That is the third equation. And the final one is simply saying that total mass should be conserved. So these are the four equations in MHD that we consider for the sun. And then we ask the questions, given these constraints, can we figure out, using the physics, what are the magnetic field sensitivity kernels such that given the observations, which are the frequency splittings or the differences in frequency, using my kernels, can we find magnetic fields inside the sun? A small caveat over here is that it's not really the magnetic field that we can find. And that is because when we look at the forces that the plasma experiences, it's not just magnetic field vector that figures in there, it's also 2 instances of B. So that's the magnetic field tensor. So this is a small side information that it's really the BB tensor that we infer and not just B. And the kernels finally are these things in yellow. So that is really the crux of my first paper. So again, in green is what we can observe using satellites. In red is what we want to find. And finally, the results of my study give the full 3D kernels for magnetic tensors. And so at this point, we can, in principle, start inferring large-scale magnetic fields inside the sun. And so what did we really do differently from the previous studies? The first thing we did was we considered that the background sun, which is this boring object that I showed you, is not in hydrostatic equilibrium, but in magnetostatic equilibrium. So it's not just pressure balancing out gravity, but it's also pressure, gravity, and magnetism, the forces of these three balancing out each other. The second thing we did, and this is okay if everyone in this room does not understand, I'll get you back on the same page in a few slides. The second thing we did is that we changed our basis to something which is a little more convenient to deal with in higher dimensions, and we take derivatives and gradients and cross products and curls and all of that. This is called the basis of generalized spherical harmonics. And so we do not deal with a scalar on the surface of the sun. It's not a temperature field. We don't deal with a vector either, but we deal with the tensors. And therefore, we changed our basis from not spherical harmonics, not vector spherical harmonics, but generalized or tensor spherical harmonics. And I show here, what I'm trying to show here is that when we make the basis change, we go into this cryptic basis where everything is written as zeros and pluses and minuses instead of easily understandable fields such as BRs, B theta and B phi. And we also show how to convert back from plus minus conventions to BR and B theta. So we have the entire theoretical prescription laid out in this first paper. And what I also want to draw your attention to is that these kernels that I showed, that I sort of showed before, that they are much more concentrated near the surface as compared to further in the deeper part of the sun. So if we look at the, where's my cursor? Okay, doesn't matter. So if you look at this part here, you see that this 10 power minus 7, much closer to the surface from 1 to 0.9. However, if you go much deeper, it goes to 10 power minus 9. So it just shows that what really the observations pick up is signals very close to the surface and not further deeper. Although you can actually play with the different kinds of modes to focus on depth sensitive modes for lower angular degrees and shallow sensitive modes for higher angular degrees. If you remember, these rays that were going right through the center were lower angular degrees, and so therefore they're sensitive much closer. So they're sensitive much deeper as compared to the shallow sensitive modes. I've made a small toy problem out of this, where we start with sort of realistic, but not exactly, of course, realistic fields, and we say that if you pass this through the forward problem, so given the magnetic field, if you build the tensor and using the kernels that we defined, that we found in our study, what are the frequency splittings that we observe? And so these frequency splittings are sort of summarized in these coefficients, which essentially are the coefficients if you decompose the frequency splittings in terms of polynomials. So A0 is like a straight line, is the flat straight line, and then A2 is the parabola. And so these are different coefficients that make up the frequency splitting. And so what we find over here is that if we take the solar model, which is represented as M1, the A0 and A2 that we find are very close to what we would sort of expect. At least the A2 is close to what we would expect from magnetic fields, or what we would expect, or we see from observations. And I'll show this a little later in a couple of slides. And then what I do is I shoot up the magnetic field at the surface 10 times. And what we see then is really that this depth sensitivity comes into perspective. So the lower angular degree mode, where S S10 here is a lower angular degree compared to S110. And what we see is that as we increase the magnetic field very close to the surface, it doesn't really change the frequency splittings for a lower angular degree because that is sensitive to much more deeper insight. So what you do on the surface doesn't really matter. However, for 110, which is sensitive much more closer to the surface, in that case, the frequency splittings really shoots up. And so here what we see is that we can selectively use different modes to study the interior compared to the exterior and vice versa. In this case, we're focusing on the shallower parts of the sun. Okay. Hopefully, I could summarize what we tried to do for the first project. And now let me move on to the next one, where we extend this from the large scale magnetic fields to the smaller scale fields and closer to the surface. And this was, first of all, aimed towards plotting or finding kernels for local magnetism. And secondly, to use Slipian functions, which Frederick actually developed for a long time in solar physics. And I'll show you how that can be used to efficiently parameterize perturbations, which will lead to much more stabilized inverse problems. So coming back to the first slide I showed you, we have covered the large scale field, which is the first picture. And now let's focus on the next two ones. So the spherical harmonics, which is what we used for finding fields for the large scale. When you zoom into these pulsations on the surface, really converts into plane waves. So YLMs, which are spherical harmonics, the notation for that goes into exponentials, which are for plane waves. And so all these pulsations or ripples going around the surface just becomes standing waves going on a small Cartesian patch. The objective in this case is to actually understand what's going on under localized patches, such as sunspots. And given a localized patch, the natural thing to do when you try to decompose into certain basis functions is to decompose it in terms of plane waves, which is all these waves that's coming from different directions, trying to capture the circular or whatever other geometry you want to capture in a box where curvature is not important. The problem is that to make up a circular structure, you would need many straight lines to properly resolve that. However, we know that when we are trying to do inverse problems, the more the number of these parameters, the worse is the inverse problem, because the amount of data available is fixed. So if you increase the number of unknowns, each unknown is going to be constrained much less as compared to if you had only a single, or if you had a much lesser number of parameters. And that is where Slipian functions come in. So for the global mode coupling, this is, I think I showed you a little bit of, this is how the mathematical inverse problem looks like, but this was observation. And this was the kernels that I showed you before, and this is the magnetic field that we tried to find. However, for the local case, it looks very similar. Observations, kernels, magnetic fields that we want to find. Up till now, whatever I'm going to show is for plane wave basis and not the modification that we made. The things that I will show you that we did in this is first to find the kernels similar to the global large scale kernels however, for localized patches. And secondly, I'll show how if you use Slipian functions, this problem actually becomes much more well constrained and better parameterized. And this was achieved through the paper that came out in 2022, which was last year. So these are the sensitivity kernels for magnetic fields in the localized patch, and each of the different components over here show the different components of magnetic Lorentz stresses. What I really want to draw your attention to over here once again is that as you go towards higher and higher radial orders, and the radial orders are shown in different rows, the sensitivity increases. So once again, there is a way to selectively choose modes such that we can look deeper and deeper into the solar interior. So until now, local mode coupling, this is how it looks like for plane waves. And when, again, coming back to the coffee cup example, when we look at the effect of perturbations on the surface or these ripples or the frequencies, it's a cumulative effect of all perturbations that's inside, not only magnetic fields. So not only the cream, but also the sugar. So what we found is, if you also think about the fact that there are sound speed or thermal anomalies that's contributing to the frequency splittings and not just magnetic fields, the inverse problem has a small complication, which is the kernel or the sensitivity kernel for the part of the horizontal pressure of magnetic field, which is bx squared plus by squared, is the same as the acoustic perturbations, which means that when we try to do an inversion, it's not only the magnetic fields that we would be inverting out of this, we would invert the entire effective perturbation, which is acoustic and horizontal magnetic pressure. This is just a small side note. So we previously saw how this was the inverse problem, and in the presence of two modes that we sort of selectively choose, there's a perturbation that we want to infer, and this imposes selection rules, which says that only mode 1 and mode 2 can tell us what sort of geometry they're sensitive to. In local mode coupling, we have plane waves given by mode 1, which is k, and mode 2, which is k prime. And if you know about this integral, you know that this essentially collapses to a delta function, which says that q has to satisfy this particular relation, which is k prime minus k is q. And so what it really means is that if we try to measure perturbations of wave number q, we have to choose modes which has wave number k prime and k. And it's only the combination of this particular k prime and k that is sensitive to wave number q. So let's try to see what that really means. So this is the sunspot, and this is how the sunspot sort of looks like with magnetic fields threading outside. And if you try to see, there are fields which are sort of moving away from the radial direction. And what I would want to show you in the next few slides is, what if we try to infer only the radially outward directed magnetic fields out of local seismology? So I take the sunspot and I find the BR squared, because it's not just B, but it's BB that is sensitive. So BR squared looks like that for the sunspot. And then I take this image and I go to its spectral space, and this is how it looks like. So I do a spatial Fourier transform. And next I ask the question that if I want to infer a Q, remember k prime minus k was Q, so that was the wave number of the perturbation that I was talking about. So if I want to infer a Q, which is somewhere there, then what happens is, this is my inverse problem, and it is only the k and k prime. So it is only these two modes, k prime minus k, which satisfy that relation. K prime minus k is q1, which is going to be sensitive to a perturbation of wave number q1. Similarly, if I want to find a perturbation of wave number q2, it's only another set of modes of k prime minus k, which is going to be sensitive to perturbation of wave number q2. What this means is that if we keep using the plane wave basis, there will be all these different wave numbers, which when we try to infer would form independent linear inverse problems. However, the number of data constraints is the same. So we only have, let's say, for example, 1 million data points. And now if you end up with 1,000 of these Qs, then each of the inverse problems would be constrained by 1,000 data points. However, if we could somehow devise a method to reduce the number of inverse problems such that it's only 3 parameters that we want to infer, however, there are 1 billion data points, then it's going to be much better constrained than the current situation. And this is a problem which is almost like trying blind men trying to find what an elephant looks like, but then touching different parts of the elephant, because it's the same sunspot we are trying to infer. However, we are looking at different wave numbers separately, and each of them is inferred to a much lower precision. So somebody's going to touch the tail and think it's like a rope. Somebody's going to touch the trunk and think it's the snake. And these are not wrong, but these are also wrong, right? So moving on, how can we make it better? So this is how it looks like, this is how it looks like for plane waves. And you see that the data contains mode k and k prime. Kernels contain mode k and k prime. Perturbation contains the q, which is equals k prime minus k, as I showed before. However, if we can modify it to something like this, where the data still contains k and k prime, kernels still contain k and k prime, but the data does not contain a q, which means that we can now use all the k and k primes available to infer the unknowns instead of selectively using subsets of data. And this can be achieved if our basis function, let's say for a circular patch like the sunspot, looks like this, or maybe that, or that. And these are all circular basis functions. And I'll show you that this doesn't need to be circular, but the reason why I'm choosing them to be circular is because I'm still focusing on a case which is a circular geometry like that. So instead of taking these thousands of plane waves coming from all directions to resolve a circle, we can simply choose these three basis functions to decompose a structure which looks like that. So let's say this was our original map. We decompose them in these three basis functions. As you can see, the coefficients for the decomposition are these three peaks. And then we reconstruct it back using just three basis functions. And we end up with everything that we want to infer within the black dashed line, which is our area of interest. So we go from here to here without using 1,000 different lines, but using just three basis functions. However, it doesn't need to be a circle. It can be a cat. And because these basis functions are not only defined in physical space, but also in spectral space, it can be a cat in spectral space and a Hermitian duck in physical space. It can be anything. In our case, the perturbations sort of look like this. So this is an emerging active regions divergence flow map. And we start off similarly for another demonstration. We start off with an emerging active region and we draw. I literally took up a pencil and on my iPad and I drew this patch. And then these are the basis functions within that patch. And then I decompose this entire structure in these basis functions and I reconstruct it back. And this is all that I'm left with. So what this means is that these are extremely efficient in parameterizing a certain structure of some arbitrary geometry on the surface of the sun for a Cartesian box. And then over on the right here is the difference between the total map and just the perturbations itself that we're interested in. Okay, we actually used this to then infer how supergranules look like, and I'm going to spend one slide on this. So if we take the supergranules on the surface of the sun, which I showed you as are these convective cells, and then you average all of them out because we sort of expect them to have some coherent property over time. And then we use circular Slipian functions and we do an inversion. This is the image of the first successful inversion of an average supergranule for the sun. And this is currently under review. Hopefully it will come out very soon. All right, so we have seen how can we infer large-scale 3D magnetic fields. We have seen how we can extend that to a local case and find small-scale shallow magnetic fields, as well as use Slipian functions to further parameterize the inverse problem and render it much well posed. Finally, the fact that we have gone through all these exercises in the magnetic field domain sort of begs the question, okay, we know all this in terms of theory. Can we really do inversions? And as I said before, the strongest signal, if you look at the sun, the strongest perturbation or the internal structure and flow that is contributing to what goes on the surface is really through differential rotation. So differential rotation, if just imagine that to be this perturbation which sort of floods the signal, and whatever is remaining, the small crumbs in the signal that's remaining after you take out the effect of differential rotation, is what really contains the information for magnetic fields. So then what we really need to do is ask the question, is differential rotation measured adequately to the maximum precision that we can with the current state-of-the-art satellites? And that's what we did when we asked the question, how accurate are the estimates of differential rotation? So just to show what differential rotation is, if you take a ball, a regular ball, and if you spin it just like the Earth, everything moves at the same angular velocity. It all moves together. However, for the sun, it's a fluid. So all points on the surface don't, and in the interior, don't really move together. So the equator rotates the fastest. It takes approximately 26 days for the equator to go around, while the pole rotates the slowest, approximately 30 to 32 days. So the sun is rotating in a very differential way. And it's not only on the surface, it's also in the interior, as I show on this image on the left. And differential rotation has been known to exquisite precision, not only because of the kernels that were known for a long time, but also because signals are flooded with the effect of differential rotation. So what we did is we asked the question that people have been measuring differential rotation till now, and they have made a certain assumption Is that assumption correct? And I'll show you what that means. So this is another version of the plot that I showed you initially, where the solar helioseismic power spectrum is now the regions are only marked over here. It's like less complicated version of that. So what I'm trying to show here is that we have modes like this on different branches of the power spectrum, denoted by red in here. And people have been assuming when they carry out these inversions, the previous studies have assumed that these are sufficiently far spaced so that there is no resonance that happens between them. So you see that all these red dots can be collapsed back into the frequency space. And the standard assumption is that none of the two dots are close enough to start resonating with each other. However, is this assumption really true? We can see that for modes which are for lower angular degrees in the second radial branch over here, we see that the slope is sufficiently high. So we can sort of say, all right, it seems like all these modes are sufficiently spaced in the y-axis. But we slowly start seeing that as we go towards higher and higher angular degrees, and for lower and lower radial orders, which are these subsequent branches, that these dots start sort of approaching each other in the y-axis because the slope reduces. And so this means that the assumption that these dots are spaced sufficiently far from each other starts going bad. So what we do is we take the parts of the branch which is most susceptible to the worsening of this effect, and we consider full coupling. We do not ignore the fact that these modes can potentially talk to each other or can potentially resonate with each other. And so just to give an example mathematically what it means, let's say we have taken a frequency window over here, which ranges from a little less than 1.5 to a little more than 1.5 millihertz. And what we do is we take a mode which is given by the yellow diamond, and we ask the question, how does that mode interact with itself? What I'm showing here is called the coupling matrix. It is, just imagine it to be a matrix filled with numbers, and the top left box over here is the part of the matrix that contains the information of how this mode resonates with itself. So this is the case which people have been considering until now. The next thing is there's another mode which is a little farther in angular degree, where the assumption worsens a little more. And this part of the super matrix or the coupling matrix captures the effect of how this particular mode interacts with itself. This is still self-coupling. This is not talking with another different mode. It's talking to itself. It's the same mode. Similarly, a third mode talking to itself. So you see that all these three were elements of the matrix on the diagonal. However, what we do is we ask the question, how does the off diagonals look like? And that's where cross coupling or full coupling comes in, where how does this yellow diamond start interacting with the blue diamond? And because why not? Because it's in the same window of frequency that we have showed here, right? And so that fills up a certain part of the matrix which is not on the main diagonal. Similarly, a different coupling will fill up a different part of the diagonal, of the off diagonal of the matrix. So that's how you construct the full matrix, by considering not only the self-coupling between modes, but also cross-coupling across modes. What happens in this case is the problem is still conceptually simple, but it becomes very computationally expensive, because what we have to do is we have to take this whole matrix and go through an eigenvalue problem. And the typical sizes of these matrices are 15,000 by 15,000, and these are complex matrices. So it's not just real, it has like a complex or imaginary part. So carrying out an eigenvalue problem of a 15,000 by 15,000 matrix, which is Hermitian, is very expensive, especially if you want to do it through an inverse problem where the same calculations need to happen multiple times. Just to demonstrate how this matrix actually looks like, this main diagonal you see here is the self-coupling. The color axis is in log scale, so you can see that the self-coupling branch, or how a mode interacts with itself, is much stronger than how it interacts with a separate mode, which is not itself. And so in previous studies, people or the previous studies were ignoring the off-diagonal components like this patch and that patch. So it's only the main diagonal that featured into the forward problem and therefore the inverse problem. However, for us, we consider the entire matrix and we ask the question, if this is how we formulate our forward model, how much of correction do we need to incorporate in the current estimates of differential rotation? And this is how it looks like. So this is a map. The first one is a map of the surface of the sun. And on the y-axis, I'm sorry, the labels are a little small. On the y-axis is the latitude, starting from 0 at the center of the y-axis, and then going towards plus minus 90 on both sides. You see the x-axis is years. So what it means is that as you go from 1996, which was a solar minimum, progressively towards future in time, you see that there are very systematic variations in the corrections of differential rotation that needs to be accounted for. And these corrections have a very systematic variation where it's a blue patch and then it's a yellow patch in the next cycle. So it clearly shows that these corrections that you need to that we found for differential rotation is somehow correlated with the solar cycle or the solar magnetic cycle. However, the corrections are very, very tiny. So this is 0.003 nanohertz. And this is approximately 0.1% of the total differential rotation, which means that these are, for all practical purposes, it can be neglected. The way we sped up the calculations is using JAX. So we brought it down from 23 days to a single day, which was, I think, a pretty good achievement, even though we didn't use GPUs, we just used CPUs until now. And finally, the last part of my presentation is these 2 slides where what I'm showing here are the A coefficients or the frequency splittings. The data is the black dots, uncertainties are the blue error bars. And what I'm showing here in the yellow line is how much the theory can explain the data if we account for everything other than magnetic fields. And this is for a certain component of frequency splitting. This is a different component of frequency splitting. Let's just focus on the left panel here, which is A2. So for a solar minimum, where the magnetic field is really weak, we see that it basically goes through this forest of modes here. However, when we go to a solar maximum, when magnetic effects become stronger, what we really see is that all that we can explain without using magnetic fields is really different from what the data shows us. And what we also see is that there is a stronger offset as we go towards higher and higher angular degrees. And if you remember from the plots in my first chapter, the kernels were very sensitive near the surface for higher angular degrees. So what this means is that this is picking up, I think this data is picking up information about magnetic fields located very, very close to the surface. And this is a potential next study that we are currently looking into with one of my students. And we are trying to ask the question, given this measurement, given this offset, and given the sensitivity kernels that I found, and also given the fact that the differential rotation measurements are known sufficiently accurately, can we then try to find what the large-scale magnetic fields look like by using this discrepancy from data and theory? What I'm trying to show here is that these are the theoretically calculated A coefficients, A2, that I showed in the previous slide. And this is the data. And you see that the order of magnitude of A2 is very similar to the A2 that I had calculated initially. And so what this means is that our magnetic kernels are actually not really off, so they're pretty good. The fact that they are slightly different is because I made a toy model, and it's not really the actual magnetic field, but it's still close enough. All right, so we covered all the chapters. We asked the question, can we measure 3D magnetic fields? Can we then extend it from large-scale 3D magnetic fields to small-scale, shallow-structured 3D magnetic fields and introduce Lippian functions for any sort of inversions? And then we asked the question, given the fact that we know how to infer magnetic fields theoretically, how well is differential rotation known so that we can just go ahead with whatever we have currently, or do we need to make modifications? And the answer was that differential rotation is known pretty well, and we don't really need to make any modifications. So this was the motivatory slide where the reason why we should study the sun is it's closest to us, and it accounts for habitability. It has large-scale magnetic fields which impact space weather, and everything that we see outside is due to something that's happening inside. And what I found in my study was, can we find internal magnetism, the large-scale fields? Can we then extend that to finding small scale structures, which is more directly relevant for space weather events? Can we measure how well differential rotation is known up till now? Is it precise enough? And finally, what is the future direction as a culmination of all of these previous studies? So with that, I'm glad to say that I finally finished my slides. But then there's a little more, which are the acknowledgements. Everything that I've done in these 5 years, of course, I have not done everything alone. And just like the sun, if you look at the sun in different wavelengths, the sun looks very different. And so during the 5 years, there were different facets of my life, but there were different people who really helped me in different ways. So I would like to acknowledge them. So here's a picture of the sun in different wavelengths. And this panel shows the people who I acknowledge and I thank. Of course, the first person is my advisor, Aaron Trump, who was kind enough to agree for a very nice picture on the last day he was here with me. Next is Srijan, my co-advisor from India. And then Frederick, Professor Bhattacharjee. And I don't think this is very visible here, but this is Dibyendu Nandi, my undergraduate mentor. And he's really the person who motivated me towards going into magnetohydrodynamics and plasma physics. So this is a picture of me and Dian on the last day in my undergraduate university. And then my parents, this is my picture from convocation with them. Everything that I have done until now, I owe to them. Where I am right now, I completely owe to them. And then my family, my extended family back in India, who has always been there for everything and has made my life until now an extremely happy journey. And then my family here in the US, in Maryland and Penn State. And of course, my family in Princeton, which is my, which are my previous roommates that I used to live with, who were unfortunately not here. With whom I have shared amazing memories because I've lived through COVID with them. My collaborators and friends from India and from the computer science. This is Dennis from computer science. This is Tunir and Samarth from India, from TIFR, Shravan's previous students. My other collaborators, Chris Hansen and Hannah Shunker. I have not really showed my study with Hannah, but I have worked on astroseismology, which is trying to find what's inside other stars. With Hannah and with Chris, we have worked on solar supergranulations, which is the study that I showed before. And of course, now I can start with my friends. Firstly, Lucas, my office mate. I've spent 5 years with him in the office, and I can safely say that all that I know about coding, and I've learned a very large fraction of that, most of them. And so we took this picture yesterday. Apparently, we couldn't find time. We couldn't find time in the last 5 years because we were discussing a million things about math and coding and a billion things about not math and coding. And then my friends in geophysics with whom I used to hang out most often. So this is mostly from AGU and also a lot of pictures with wings because Shao likes wings. So yeah, amazing memories. I really don't think I could have gone through without my friends from geophysics. And also the extended department. Everybody in the department, I think, is in this picture, although you cannot see it. And if you have missed out in any of these pictures, that's because you were too busy with generals. I'm sorry, Will. The new postdocs that I've got so well along with. Yeah, it's basically a family for me over here. And then finally, I cannot really finish this without thanking the administrative staff in Princeton, Cheryl, Mary Rose, Doreen, Nora, Georgette, Mike, Kari, and Elada, all of whom have played such roles, which, at some point I feel like it's not noticeable, but now that I think about it, it has really made all the difference where I don't need to worry about anything other than just putting my head down and working. So I have my work and everything that I've shown you until now has involved participation with collaborating institutes like TIFR, NWRA, Max Planck, University of Newcastle, Australia, NAO, Japan. And my work, parts of my work were either through summer schools, conferences, and awards were funded through the Living with the Star program of NASA, the Elizabeth H. and Dallin FA Award, the Indian Institute of Astrophysics, and the Kavli Summer Program in Astrophysics. And finally, after all of this, I would like to leave you with a slide which sort of summarizes everything that I've talked about. Feel free to ask questions.
Thank you, Srijan. Let me clarify that we'd like to open the floor to questions from the general public that isn't the jury for 2 minutes, as many as there are. Then we will all take a break to get some coffee with cream and sugar. And then the jury will come back and question the candidates some more. Now, it's an open public defense, which means that the general public can stay beyond, but nobody ever does, and you really don't want to, okay? But those of you that are on Zoom, you have registered, we have your email, and when the jury at the end then comes back to deliver the verdict, we will send you, Mary Rose will send you an email alerting you that you're welcome back into the room. So, questions from the public audience here about the presentation or beyond?
Top right, I think you have the same slide as slide 32 or
Mhm.
something. The outline of the black outline is basically capturing the zero.
Wait, let me go back.
Yeah.
Oh, too far. Okay. All right.
So in panel A,
Mhm.
the black outline basically outlines zero, like, you know, if it touched the non-zero part, and when you try to recover it, how is the liquid very fun?
Oh,
Now basically you have no liquid, like, you basically fully recovered.
so the thing is, I didn't try that, and the reason is that this outline that I draw, so we have to remember that when we draw this outline, we know nothing about what's underneath. So the inspiration of drawing this line is what we see on the surface. So we'll of course try to capture all the features and not cut through a certain feature. So it'll always pass through a certain place which is very low magnitude or close to zero. However, if it goes through it, what will happen is that we can still capture it, but it will still be fine, but we'll have to go to much higher number of basis functions. Because if you look at the very first basis function, the simplest one, you see that the function is not really touching the periphery of that margin, the very first one. But if you go to progressively higher ones, it's starting to touch the margin and also leak outside a little bit. And so if our feature or if our domain is cutting through a certain patch which is non-zero, to resolve the part which is actually cutting through the main structure, we'll have to go towards higher number of basis functions. It'll still be able to capture it. The number of parameters will be high, which will sort of defeat the purpose of trying to efficiently parameterize the system. Sam.
Good call. So I'll put a question about this one.
Yep.
So if you like took a metal plate, you cut it out in that shape,
Mhm.
and you sand on it and grind it, would you expect to?
If you put some sand on it and then what?
Yeah, some sand on it, and then you would like grind it
Like in a science museum when you hit
Oh, okay.
yeah, from.
Uh-huh.
Would you expect to find we can choose an active site each of these basis function modes, or are they sort of just like an efficient, objective way?
Yeah, I
of
wouldn't
creating
expect.
your thought?
Yeah, no, I wouldn't expect the sand to redistribute itself in this basis functions, because these basis functions are, I think, a numerical construct. It doesn't know about the physical property of that plate itself. So what you're talking about is the natural frequency of a certain object, but this is something purely out of numerics, which doesn't know about. Yeah. Well,
Yeah, thanks. So it sounds like you kind of got the theory covered, but your kernel is the better and worse problem. What if I know that you're not staying in stuff now, the stuff now, but if you were, or if there were other students who can go forward, what's the next big constraint? Is it computational or is it observational?
you mean what is the next step or what is the challenge?
Yeah, what's the next step? What's the next biggest challenge associated with that?
So it is this plot here,
Yeah.
where we see that everything other than magnetic fields don't explain what's happening with the yellow line. And the data clearly shows there's a very clear trend. And the fact that it is increasing towards higher angular degrees means that there's something very close to the surface, which we're not accounting for, that is getting recorded in the data. And that's something, what can it be if there's a difference that drastic between solar minimum and maximum? We think it is this magnetic field. Yeah. No, we just need to take these dots. We use observations equals integral kernel times perturbation. We feed in these dots in the observation. We feed in my kernels in the kernels. And then we use an inverse problem, a linear inverse problem to find the perturbations. Hopefully, if the data is enough, signal to noise is not that large. Sorry, is not that small. We can make some estimates of magnetic fields in the near surface shear layer. The near surface shear layer is something that extends from solar surface to 0.95 solar radii. So I think that's where these things will come in, because these are very large angular degrees, which is shallow structure. Please go ahead.
This yellow line, is that first order?
No, so this contains first order effects such as just differential rotation itself, and as well as mode coupling, which is the small corrections from the eigenfunction correction.
Mode coupling, is that treatment of that? Is that first order?
Oh yeah, these are all under linearized for.
So basically, what you're saying is that you can use first order rotation theory to explain this large difference. That's what you're saying.
The first order perturbation theory in magnetic fields to explain the difference. Yes.
That these perturbations are small enough.
Oh yeah. So the solar helioseismic spectrum is known so well that we have to, I've not put that plot, but we have to expand the error bars 500 times to see the error bars. So they're already very close when you compare the background solar model with what you observe. And therefore, the differences are so tiny that they can actually be treated in the regime of linear perturbation theory. Thank you. Alan.
Question about granules and supergranules.
Mhm.
So can I think of the granules as individual convection cells?
Yep.
And do they have a consistent sense of up in the middle, down?
So hot plume, hot stuff going out from the center, and then going colder, it radiates out the heat and it goes down as cooler plumes from the periphery.
And the supergranules, does that just take a certain number of granules and you average them, or is there actually a physical way in which granules close enough together behave?
Yeah, good question. I think it's the sorry. I think the supergranules are the structures where you have a central large scale field that plasma moving upwards, and then the rest of it is going downwards. I think the granules are much shallower than the supergranules, and they're much tinier, so that effect sort of gets averaged out when you look at the scale of a supergranule. So whenever you look at a structure which is very tiny, I think the extent of that is not too far compared to something which is larger. So supergranules are these much larger structures on the surface, whereas granules are much tinier. And at the
You really just separate them. They seem to separate
in spatial scales there. Yeah. Thank you.
So my questions are mostly related to disclaimers that you might want to talk about a little bit. So when you're talking about localized flow or some sort, and you're using setting functions, it seems a little bit magical, right? Like you can actually reduce the number of functions. But underlying all of that is an assumption that you have to use an Lmax, right? The
total number of
Yeah.
basis functions.
Yeah.
Yeah.
So that will have, is there an understanding of how much you can believe the variations at different wavelengths, such that uncertainty in the measurements, that you can actually make a shape like that? Because when you're making a local region, you're also making an assumption about how much you believe the data at that Lmax wavelength, right?
Oh,
Otherwise, the shape should be fuzzy.
so you're saying that do we believe all the tiny details?
Computing
Yeah.
harmonics up to-
Are you talking about spherical harmonics or are you talking about Slipians?
I thought it was seconds, but when you're building the second,
Mhm.
go up with a number of these, right?
Yeah.
Just inherently how many sort of one green sort of harmonics.
Oh, so you're saying, okay. Okay, so let's say you're trying to resolve a structure which is as tiny as Sri Lanka using spherical harmonics. It has to be much, much larger as compared to if you take a map of Sri Lanka and build Slipians on that. So I think we are talking about differences of the order of 50 times at least.
My question is, do we know, in your example, Sri Lanka, do we know the variations on this, the observations up to that wavelength? It's sufficient value.
Oh, yeah. So we make these things called local correlation tracking images, LCT, and the pictures that I showed you, one of them was from there. And so we do observe them pretty precisely to be able to do that. Yeah.
Okay. So thank you very much. Those of you who are remote, we are going to take a 5-minute break, bathroom break or coffee break, and then we'll reconvene in this room for the rest of the questions.
Would you like to talk to that? Certainly.